You know, deep learning often feels like a kind of magic, doesn't it? We have these massive models that seem to just break all the rules we thought we knew about machine learning. But what if that magic is just an illusion? Let's dive in and see if we can pull back the curtain on some of deep learning's biggest mysteries. I mean, when these huge neural networks started hitting superhuman performance, the reaction from a lot of researchers was basically this. The models were just so big, so powerful, and so darn effective that they seemed to fly in the face of decades of wisdom about how machine learning was supposed to work. But here's the really provocative idea from the research we're exploring today. What if the old textbooks weren't wrong? What if the core principles that explain why deep learning works have actually been around for decades, and we just needed to start looking at these incredible new models through the right lens?
To figure this out, we've got to start by understanding the magic tricks. We're talking about the three big phenomena that make deep learning feel so strange and different from everything that came before it.
Okay, first up, we have this puzzle called benign overfitting. This is where a model perfectly memorizes its training data, and I mean everything, every single example, including all the noise and even totally random labels. But somehow that perfect memorization doesn't completely wreck its ability to make good predictions on new data.
And this is where it gets really, really strange. Imagine you're training a model on images, but you've secretly replaced a bunch of the correct labels with random ones. The deep learning model just learns them all. It gets a perfect score on this noisy, garbage training set. Now, according to classical theory, its performance on new, real data should fall off a cliff, but it doesn't. The error goes up a bit, sure, but it doesn't explode. This just shouldn't be possible.
The second puzzle is this thing called the double descent curve. And this one really seems to bend the rules of logic. We were all taught that there's a sort of Goldilocks zone for model size. Too small and it can't learn, too big and it just overfits. A simple, predictable, U-shaped curve. But this is what we actually see in the real world. As we make a model bigger, its error on new data, we call that the test risk, goes down, then it goes up as it starts to overfit, just like the textbook says. But then, and this is the wild part, as we make it even bigger, the error starts to go down again. That second drop is the double descent, and it suggests that after a certain point, making models bigger actually helps them generalize better, which is just deeply counterintuitive.
And that leads us right into the third mystery, over-parameterization. This is just a fancy way of saying that the most successful deep learning models have millions, sometimes billions, of tunable parameters. That's often way more parameters than there are data points to learn from. So the question is, how can a system with that much freedom avoid just finding some ridiculously complex solution that only works for the training data?
So, right, we have these three baffling phenomena. The research we're talking about today argues that you can understand all of them through one single elegant concept, the idea of soft inductive biases. This is the key. This is what unlocks the whole thing.
Okay, so what's the difference? Well, the old way of thinking, what we can call a restriction bias, was like building a small fence. You strictly forbid your model from doing complex things. A soft inductive bias is totally different. It's like you open up this massive, huge field where the model can represent any solution it wants, complex or simple, but you gently encourage it. You create a preference for the simpler ones. And this visual just illustrates the idea perfectly. A restriction bias, that's on the right, it just chops off huge parts of the solution space. But a soft bias, there in the middle, keeps the space enormous, but just kind of shades it with preferences. It's like creating a landscape where the simple, good solutions are down in these wide, easy-to-find valleys, while the crazy, overfitted solutions are way up on these steep, hard-to-reach peaks. The model can go anywhere, but it's naturally guided to the good spots.
So, the most important point is this. A soft inductive bias is a preference, not a prison. It's a way to guide an extremely flexible model towards solutions that are more likely to be good, without ever sacrificing its power to capture real complexity if it needs to. Let's make this really concrete. Imagine we create a ridiculously powerful model, one that can draw insanely squiggly lines. By itself, it would overfit everything in sight. But now, what if we add a penalty, a little cost that gets stronger for the more squiggly parts of the line? What happens? Well, now the model will always try to explain the data with a simple straight line first. It only pulls out its complex superpowers if the data absolutely forces it to. That right there is a soft bias in action. Okay, so now that we have this key, this idea of soft biases, let's go back and see if we can finally unlock those three mysteries. And here it is. This is the big reveal.
That strange double descent curve we saw with those complex deep neural networks? Well, it turns out you can reproduce the exact same pattern with a much, much simpler linear model. This is the smoking gun. So what this means is, if a simple linear model shows these same weird behaviors, then they aren't deep learning magic at all. They are the natural, predictable result of a general recipe for learning. Take an incredibly flexible model and combine it with a soft preference for simple solutions.
So if these phenomena aren't actually unique to deep learning, then what is? If we strip away all the supposed mysteries, what really sets neural networks apart from other models? Let's take a quick look at what the research actually points to.
Well, the paper highlights 3 things that are pretty distinct. First is representation learning. That's the model's ability to figure out on its own what makes 2 things similar for a given task. Then there's universal learning. This incredible fact that a single architecture, like a transformer, can master language, vision, and more. And finally, there's a very strange and fascinating property called mode connectivity.
This next idea really turns a classic assumption on its head. So think of all possible solutions for a model as a landscape, right? Where low valleys are good solutions. We used to think this landscape was full of isolated little valleys, and training was just about finding one of them. But mode connectivity shows that, for neural nets, the good solutions, the bottoms of all these valleys, are actually connected. They form one giant interconnected continent of good solutions. And that seems to be a very unique property.
So let's wrap all this up. What is the single biggest lesson here? What does this all mean for how we should think about building intelligent learning systems in the future?
The ultimate takeaway is really this. The secret to building models that generalize well isn't to put them in a straitjacket. It's not about restriction. The real recipe is to give them immense, almost unbounded flexibility, but to combine that freedom with a gentle, soft preference for simpler explanations. And this leaves us with a final, really provocative question that goes far beyond just deep learning. If the secret to the powerful intelligence we're starting to build isn't about rigid constraints, but about creating these vast, flexible systems that are just guided by simple preferences, what else could we build with that principle? What other problems could we solve?